In the last session, we talked about the construction order, the role of the temporary steel tower, and the mock-up test before the actual dome was built. Temporary steel towers were important for carrying loads of up to 280 tons at one point, so they had to be positioned accurately without a 10mm fine error. In addition, before making an actual dome, we conducted a 1:33 scales mock-up test to check the details of light, temperature, and microclimate using our actual materials. The full-scale mock-up tests provide the reference point for continuous reference during the design period, including cladding prototypes, finishes, joints, and fabrication test procedures. After completing these considerations, they are ready to build the dome. From now on, we are going to talk about all the stories of the dome. Jean Nouvel thought that Arab architecture was always associated with light and geometry. To create a beautiful rain of light, the engineering team carefully designed thorough digital modeling for each challenge. Symmetry was also important for the four huge concrete piers to the detail of the single star. Eventually, they completed the current model by changing the shape of the pattern and the layering of the pattern in the 23rd model. For example, they are arranging triangles by changing sizes and densities. The Dome of Louvre Abu Dhabi has a complex geometric structure consisting of 7,850 stars in 8 different layers. 4 outer layers clad in stainless steel and 4 inner layers clad in aluminum, separated by a steel frame 5 meters high. The pattern is repeated at various sizes and angles in the 8 superimposed layers. None of them is identical and they are achieve gradual transformation. As you see, these following 4 cladding layers have each different scaling, rotation, and densities. The concept of lighting studies for the density was provided by museum building with maximum amount of daylight on the glass roof while water and public plaza areas should be in the shadow. The galleries were intended to have a daylight factor of 10%. The plaza was intended to be well protected, while the water surface and the other buildings were slightly less protected. And the following study speed map of the site defines the density of the light at 8 to 0% ideally. And when it translated into geometry, as you see, the density of the dome is less than on the edges. The 3D model visualization to help understanding of the actual fabrication describes how each layer joined together with pre-installed connector at the intersecting position of next layer. The dome structure was intended to use a light-based parametric design framework. The result is a cinematic effect as the sun path progresses throughout the day. At night, it forms 7,850 stars visible from both inside and out.
I will explain the construction of Louvre Abu Dhabi Dome. The Dome of Louvre Abu Dhabi is different from the commonly known dome. A typical dome is a 300-degree rotation of the arch. The load on the arch is to send what is received above along the curve. Therefore, the dome also receives and distributes the load in the vertical direction of the circumference. However, the dome of the Louvre Abu Dhabi has only 4 permanent support towers in the direction of carrying load. Due to this load transfer problem, the structure design team in Louvre Abu Dhabi made the dome into a double symmetric structure and controlled the number of nodes comprising it. As the design developed, drawings were created to describe in detail the metal-coated member and connection of the entire dome. The dome's construction documents were fully automated from these detailed studies, producing detailed drawings of more than 300 pages and quantities of 3,000 pages. Based on this, the actual dome construction began. In the second week of December 2013, a giant 87-meter mobile crawler crane appeared. The crane's role is to raise the steel frame, which is a component of the dome, and put it on a temporary steel tower at speeds of up to 1 km per hour. There are 85 steel frames in total. Each thing has 30 to 70 tons and made of more than 100 scale-shaped steel. But there was a potential disaster in this work. The weight of the steel frame, a super large component of the dome, was similar to the crane's maximum lifting capacity. Therefore, there was a risk that the crane would fall forward due to vibration while carrying this super large steel frame. There was also a possibility that the temporary support base would collapse under the weight of the crane if it was moved close to the place where it was transported. To solve this problem, the safety of the crane was continuously monitored by satellite connected with German manufacturer, and super large element could be placed in the desired location. The dome work was accelerated as the first super large element was fixed to the location of temporary support tower. At the top of temporary tower, a huge segment of dome was temporarily supported on metal boards and socket props. Based on the steel frame of each temporary tower, a bow-tie-shaped steel frame was installed at the center, and the shape of a dome was created by connecting each steel frame. A 600-ton crane was used to construct the dome section closest to the outer edge. As construction began in the center of the dome, the components of the dome were inserted using crane with a capacity of more than 1,600 tons. A total of 85 super large elements were all fixed in place, and 120 temporary towers supported the structure to create a steel breast. After all the dome structure were connected, the dome was lifted 38 cm using 32 hydraulic jacks with a lifting capacity of 310 tons. After the dome structure was raised, temporary joints were removed and 4 of 6-ton bearings were installed as permanent supports. The bearings include isolator and spherical sliding bearings. Isolator allow the structure to move under the dome when the earthquake. Spherical sliding bearings can withstand temperature changes during the day and night under the hot sun. After the bearing was settled, the structure slowly built on the permanent support tower.
In this session, we learn more about the overall shape of the dome, the shape of the structure of each layer, the structure of the stars. In the next time, we will talk about the amount of sunlight that the dome structures controls, the energy consumption of the building, and the environmental microclimate. Let's also talk about how things that are controlled by the dome and are controlled by the different uses, such as museums, squares, and the rest areas under the dome. This is the end of the presentation of the Team 3. Thank you.